The next talk is by Benedikt Riedel from IceCube, and we'll be talking about planes, satellites, trucks, ships, and fiber optics, how to manage data coming from the bottom of the world. Take it away, Benedikt.
Sure, I hope you can see my slides. So just briefly, I'm going to go through a little bit of background. So first of all, what is IceCube? IceCube is a neutrino telescope that we constructed at the Adams and Scott South Pole Station in Antarctica. We picked this site mostly because there's infrastructure there, but also building a detector the size of IceCube. So the name kind of hints at it, but it's a cubic kilometer of ice instrumented with what we call photomultiplier tubes. Would be prohibitively expensive if we do it sort of in a traditional way, which would be building a cavern in a mountain and instrumenting that, basically. I mean, this is something that they do, that we've done, that has been done in Japan, or is being also, and they continue to be done in Japan. But I mean, ultimately, these experiments are much smaller and focused on a different science goal than an IceCube. So the main physics goal here is to observe high-energy astrophysical neutrinos, meaning neutrinos or subatomic particles that come from, your favorite astrophysical source. So anything from, a galaxy to a solar system or things like that. And this is really what we're looking for. And you need a large detector for that. So it's the location. But then and to instrument that ice, we used something called digital optical module, which is basically just a light detector with some RIA electronics attached to it. And then basically we drilled holes into the ice that are about 2 miles deep, and deployed these what we call strings of detectors into those holes, and basically build a detector by drilling 86 of these holes and overall. From a science side, IceCube is a fairly novel instrument. I mean, as you can tell, it's built around building in the ice. We're using a natural medium, which is sort of novel in that sense. It's in the size of the instrument, it's also fairly novel. But we also have very broad science abilities, just not or science capabilities, let me put it this way. So we focus on astrophysics, sort of our flagship, but we also do a lot of sort of fundamental physics, particle physics research in neutrino physics, beyond the standard model research, dark matter searches, and then also so fundamental symmetries, meaning that we can test fundamental ideas of the universe, or that theories of the universes that we have. And then similarly, with our detector, we also do some earth science in terms of glaciology. So we have, for example, studies of how the ice was deposited, and how the pressure of that deposition has changed the ice, but then also atmospheric science. So there are changes high up in the atmosphere that we see in our detector with the data that we record. And ultimately, Earth tomography, we see particles that are traveling through the Earth, and their ability to travel through Earth is kind of dependent on the Earth structure. So ultimately, we can do some level of tomography there. So as all of this sort of comes in, there's a lot of different ways that we process data, that we use our data. And a big part of this is also simulation, where we basically, as a traditional sort of particle physics method, is you compare data to what you expect from simulation. So you have sort of a theory, and you simulate that theory in an idealized detector, and then compare that to what you actually have in data, and then you draw conclusions from that. So why are we actually doing neutrinos? So this is a little bit of a Hail Mary in some respects. originally to a problem of where do cosmic rays come from, which are charged particles that interact with our upper atmosphere, and they constantly bombard the atmosphere and also the planet, and we just don't know where they come from. And a big problem with that is their paths are changed by magnetic fields, and the universe in of itself is sort of a magnetic field, but also as they travel closer to objects and things like that, their paths get deviated, so we don't have really a good pointing back. The other big piece is that at the highest energy, so very energetic, very catastrophic events, and at the longest distances, the universe is dark to us in some respects. So traditional astronomy, your telescopes on mountains, your radio telescopes that VLA and things like that are dark in some respects, meaning that they can't actually probe these areas. And you sort of the only other source at this point, or the only other way to look at these sources or these areas that are sort of terra incognita, are gravitational waves, which at the moment can't probe that far out in the universe. But we do have folks, or our friends from LIGO, which are going to talk as well today, are trying to sort of probe there or closer to this area as well. So ultimately, the solution is that we need new sets of messengers. So traditional astronomy way, or a new set of probes into the universe, because the traditional astronomy has sort of reached this physical limit in some respects. So giving us a brief history of neutrino astronomy in Antarctica. So this whole thing started around 1988. And since then, we've worked steadily with precursor experiments like the Amanda, and then IceCube itself since 2011. And since then, we've made multiple sort of groundbreaking discoveries of basically high energy neutrino astrophysics, or high energy astroparticle physics. So we found high energy astrophysical neutrinos. We have our first sources, so we know that these particles come from certain subsets of astrophysical sources. We've done some particle physics in that we tested particle physics at very high energies, which very few experiments can do. And of course, now we're moving sort of into the precision measurement phase in some respects, with all of these discoveries. So this is just a sort of high-level summary of what our data workflow, or our data flow looks like. I mean, the big thing I want to take away here is sort of we're split in many ways between the online piece, which happens at the South Pole, which we have to do at the South Pole because of limitations to networking. We don't necessarily have a sort of a big pipe of data from or a big network from South Pole to the coast and then to another continent. And similarly, the work doesn't stop at the South Pole. It goes on in the north, what we call the north, which is anywhere outside of Antarctica, basically, where we do science in that respect with that data. And also we have a piece that is a big community piece, where now with these multi-messenger astronomy or multi-messenger astrophysics, and the alerts that we kind of send out, that we communicate a lot with the community. If you look under the hood of this diagram, it looks something like this. These are some of the gory details that I just wanted to show, that this is sort of not necessarily a straightforward thing, but we have multiple data paths, and they go to various different places depending on the data and what exactly you're doing. But this is sort of just an overview that this is sort of not, this is what I'm talking about is very, very high level. So sort of just talking about data routes in general. So we have three major data routes that I have I sort of summarized here. So there's our priority data, which is mostly the alert data. and some high-level monitoring data, just making sure, the detector is still running kind of thing. It's really, I'll go into the details. Then we have our filtered data, which basically is just a subset of data that's in a lossy compression. And once a year, when we do have access to the experiment, we basically retrieve archival data, meaning we have a set of disks that get filled throughout the year with all the data that the detector records and then gets shipped again to UW-Madison to then be distributed into our archives. But then also I want to highlight, all this goes through UW-Madison, but ultimately, there's also pieces in the community that are very strong. So, for example, the General Coordination Network from NASA, that's a collaboration between NASA and NSF that's being built right now. Then we have, our friends that do archival at NERSC and TAC, and then we also have our international collaborators at DAISY who also do some of the archival work for us. Sort of highlighting a little bit, going through these individual data routes. So as I said, these are what we call priority data stream, but ultimately it's an alert data stream that we basically created to make sure that we can communicate with the local experiment operators. We have 2 folks that are on station 365 days a year, basically as sort of experiment operators, and then we have communication monitoring over that stream as well. So this is basically a phone line. Ultimately, think of an old modem, but this time it goes over satellite. We can do emails with small attachments, but not much more. And ultimately, we have to within that compressed data stream, we send alerts and basically, updates on the detector saying, detector is still up, everything is going fine. But the key piece here is that, we're routing all of this then through UW-Madison and then ultimately out through a community network to our partners that they can follow up on our observations. So we have done this, and I'll go into details on that in a second. And then also, they get information, nearly at the speed that we do. And all of this usually takes about 30 seconds from observation to an alert or a message being sent out. Sort of going a little bit more into the details here. So multi-messenger astrophysics, basically what we're doing is we're observing an astrophysical phenomenon with more than one messenger. Messenger here is sort of a group term between, our classical astronomy with electromagnetic waves, gravitational waves with LIGO, and then us with neutrino. It was one of NSF's big 10 ideas. Ultimately, it means, traditionally we've observed everything in electromagnetic regime, but now we have these other options with LIGO and IceCube to expand that as a thing. We've actually done this from this blazar. I'm not going to repeat the name ultimately, but we had a detection or we had a neutrino that pointed at this source, and then over the course of roughly a month, we had follow-ups from a variety of different space-based and ground-based observatories and different electromagnetic observatories, and then basically it showed that this source was flaring or that it was having a higher activity than normal. And basically this was our first high energy point source, meaning that we have a single thing or a single object that we can trace back in terms of our detection. This whole thing was initiated by IceCube and then followed up, as I said, by multiple other observatories. And ultimately, this is the small data that comes in here is still very important to us to make these observations. And it's a time sensitive endeavor at this point. Similarly, then, you can go back in through our back catalog of data and see, this source has actually flared before in comparison. to its base level. But ultimately, I mean, this is something that was completely initiated by this one observation that we had there. For our filtered data, we basically get sort of a daily large-scale trough of data. So this is shared between us and other experiments at the South Pole, mainly the South Pole Telescope and another experiment called BICEP. So once a day, roughly, we have a connection that has a roughly a bandwidth of 500 gigabytes a day, out of which we get about 110 gigabytes a day is allocated. So what we do is from all the data that we collect, we apply a lossy compression and do a very sort of I wouldn't say arbitrary, but very high level cut on that data. So we perform, you know, a lot of the lower energy data that makes up a bulk of our of what we record is kind of is scientifically difficult at the moment to separate from, you know, to separate the signal from the background. And ultimately, you know, that is so we made that decision to kind of focus on higher energies or relatively higher energies at that point. So we apply this lossy compression to fit it into our allocation, and then we also sort of add a set of monitoring data, more detailed monitoring data to that data set in order to you know, have a better view of the detector, and then make sure that we can understand what happened over time with the detector. Ultimately, this is our first step of storage is at UW-Madison, but we also immediately make a copy at the Daisy Zeuthen, which is in Germany, to basically have a backup in case something happens at UW-Madison and we need to recover. You know, we have a disaster recovery option that kind of happens automatically as data arrives. So given this data, we were able to basically identify two large sources or two sources of high energy astrophysical neutrinos. First, we used some what I would like to call line-shaped events. Basically, they're literally a line through a detector that have a very specific location, or that trace back to a very specific location in the sky. And we basically said, you know, you check all locations in the sky and see if there's one above threshold. So you can set that that is a very statistical threshold in that respect. This is a purely statistical analysis in the sense that, you know, we have all the data and we go through all the data and then say, okay, is there a spot in this sort of sky map or in the sky that we have resolved that is above a certain threshold, given our sort of statistical tests and things like that. And this way we found our second high energy neutrino point source, which is NGC 1068 or Mercier 77. And this is basically saying, you know, we have something that constantly is an emitter of high energy astrophysical neutrinos. The second big thing that we saw is actually our own galaxy. So our own galaxy is a little bit shadowed because of all of our background. And ultimately, you know, we're using these ball-shaped events, so they have very low pointing resolution, but they're good for these broad or big sources like our galactic galaxy. And one thing I would like to highlight here is that, you know, this required some work with machine learning to be able to reconstruct these events. And ultimately, you know, we found a third neutrino point source, which is our own galaxy. And the last path is kind of the planes, trains, and automobiles path that I hinted at in my title. As I said, you know, yearly we basically ship all the data from the South Pole to the North. It arrives in disks. We ship disks back and forth basically, and it goes from the South Pole to the coast to the coast. Then from the coast it goes to New Zealand, and from New Zealand it goes onto a ship. And then from the ship, it arrives in a port in the US and then gets trucked to UW-Madison, where we basically take it again, take the disks, copy them, and then ship all the data off to NERSC. and TAC for archival. And one of the big key aspect of the data is allow future processing. As we learn more and more about the detector, especially since it was built in a natural medium, you know, we don't know necessarily all the properties a priori. So as we update our detector understanding, we need to reprocess the data and potentially refine our analyses and refine what we found. There's a lot of potential to find new results, especially since it's such a novel experiment. We're doing sort of very cutting edge science here. And ultimately, to draw sort of the comparison here, there's a big question mark here. You know, there's beyond the standard model physics. There's a lot of different theories out there of how particles behave, and we know that there are things missing from our picture of the universe, or the picture of the universe. There's also, you know, can we improve our sensitivity? Can we find other sources with better data reduction methods, with more analysis methods, and especially machine learning? There's sort of like, you know, the reinvigoration, especially now with machine learning, that, you know, we can do more with our data than we have done before, and very much we're in that mode right now. One brief thing that I also wanted to mention, since this is sort of crucial to any physics analysis or any data analysis in IceCube, is our simulation data. So to briefly go into this, what we do is we compare data to simulation. We have a theory, we produce events, we solve the forward problem, and then basically we try to solve the inverse problem from knowing that. So this is very much sort of particle physics, or this is normal in particle physics, but ultimately this is also involves what they call a simulation, and the data that, you know, is created by that simulation, or the artifacts that are created by that simulation, and these are also basically run through our entire data warehouse here, in that we store this, we produce this data, or these artifacts, and then we have to transfer data in and out of our data warehouse to be able to go through different steps of refining them and simulation steps. But ultimately, the big takeaway here is this is data that is reproducible, and we do not archive it or anything. We just produce it and basically use it for a time and then throw it away. But this is the key piece. But ultimately, this is also a key piece to any analysis in IceCube, that we need to solve the forward and the inverse problem at the same time in some respects. And that's it from my side.
Thank you, Benedikt. Any questions for Benedikt?